What specific problem does your method aim to solve in the context of nearest neighbor search, and how does it differ from traditional data structure approaches?
Our method aims to solve the problem of nearest neighbor (NN) search by allowing deep learning models to discover entire data structures and query algorithms in an end-to-end manner, rather than relying on hand-designed structures. Traditional approaches typically involve predefined data structures, such as binary search or KD trees, which are designed to be worst-case optimal and do not adapt to the underlying data distribution. In contrast, our framework employs a data processing network to learn how to transform a raw dataset into a structured database, while a query execution network learns to efficiently query this structure. This joint learning process enables the model to exploit distributional properties of the data, leading to improved performance over traditional methods, as evidenced by our model outperforming binary search and KD trees in various settings. Ultimately, our approach eliminates the need for expert knowledge in data structure design, allowing for a more flexible and adaptive solution to NN search.
How does the proposed algorithm for data structure discovery work? Illustrate the steps involved in the data processing network and the query execution network.
The proposed algorithm for data structure discovery operates through two main components: the data processing network and the query execution network. The data processing network transforms a raw dataset, D, into a structured database, HAT-D, by first ranking the elements of D using an 8-layer transformer model, which outputs a scalar rank, O_i, for each point, X_i. These rankings are then sorted using a differentiable sort function to produce a permutation matrix, P, which reorders the dataset into HAT-D_P. Additionally, the network can output extra vectors, B_1, L.B_T, to enhance the data structure, resulting in HAT-D equals HAT-D_P B_1, L.B_T. The query execution network, on the other hand, is responsible for retrieving an approximate nearest neighbor from HAT-D, given a query, Q, and a budget of M lookups. It consists of M individual query models, Q_1, L dots, Q_M, each producing a one-hot vector, M_I, that indicates the lookup position in HAT-D. The model computes the value at the lookup position and uses the query execution history to inform subsequent lookups, ultimately outputting the nearest neighbor prediction, HAT-Y, based on the retrieved values. This end-to-end training ensures that both networks are optimized for their respective tasks, allowing for efficient data structure discovery.
Can you describe a simple illustrative example that demonstrates how your algorithm constructs the data structure and retrieves the nearest neighbor?
A simple illustrative example of how our algorithm constructs the data structure and retrieves the nearest neighbor can be seen in the one-dimensional nearest neighbor, NN search scenario. Initially, the data processing network learns to sort a dataset, D, by outputting a ranking for each element, which is then used to reorder the dataset into a structured database, HAT-D. For instance, if the dataset consists of points sampled from a uniform distribution, the model effectively sorts these points, achieving approximately 99.5% accuracy in positioning them correctly. When a query, Q, is made, the query execution network utilizes this sorted structure to perform lookups. It learns to start its search closer to the nearest neighbor based on the distribution of the data, outperforming traditional binary search. This end-to-end training allows the model to adaptively learn both the sorting and searching processes without explicit supervision, demonstrating its capability to construct efficient data structures and retrieve nearest neighbors effectively.
What are the empirical advantages of your method compared to traditional methods like binary search or KD trees, particularly in terms of efficiency and accuracy?
Our method demonstrates significant empirical advantages over traditional methods like binary search and KD trees, particularly in efficiency and accuracy. For instance, in one-dimensional nearest neighbor search, our model learns to sort the data and adaptively search, outperforming binary search by exploiting the underlying data distribution, achieving approximately 99.5% 5% accuracy in sorting and better query performance. In two-dimensional settings, our end-to-end model achieves around 75% accuracy compared to 52% for KD trees, as it effectively learns to position points close to each other based on their distribution, rather than relying on fixed partitioning. Additionally, in high-dimensional data, our model learns representations that facilitate efficient nearest neighbor search, competing well with locality-sensitive hashing methods, which are traditionally used for such tasks. Overall, our approach not only improves accuracy, but also enhances efficiency by dynamically adapting to the data distribution, eliminating the need for hand-designed structures.
How was the effectiveness of your proposed method evaluated? What datasets and metrics were used to validate the performance, and what were the key findings?
The effectiveness of our proposed method was evaluated through experiments on one-dimensional, two-dimensional, and high-dimensional nearest neighbor search problems, using datasets sampled from various distributions, including uniform, Zipfian, and hard distributions. We primarily measured performance using accuracy, defined as the 0-1 loss in identifying the nearest neighbor after each lookup, and compared our end-to-end, E2E model against established baselines like binary search and KD trees. Key findings revealed that our model learned to sort inputs with approximately 99.5% accuracy in 1D, outperforming binary search by exploiting data distribution knowledge. In 2D, the E2E model achieved around 75% accuracy, surpassing KD trees, while in high dimensions it demonstrated competitive performance against locality-sensitive hashing methods. Additionally, our framework was successfully adapted to frequency estimation tasks, outperforming the count-min-sketch algorithm, showcasing its versatility and effectiveness across different data structure problems.
What limitations did you encounter with your method during experimentation, and how might these limitations affect its practical deployment in real-world scenarios?
During experimentation, one significant limitation encountered was the model's performance on hard distributions, where the nearest neighbor's position in the sorted data lacked a strong prior, making it challenging for the model to learn effective search algorithms. This resulted in the model discovering a search algorithm similar to binary search, which, while effective, may not be optimal in all scenarios. Additionally, the end-to-end learning framework, while promising, lacks the provable guarantees that traditional learning-augmented data structures provide, which could be critical in applications requiring reliability and predictability. Furthermore, the model's reliance on the underlying data distribution means that it may struggle in dynamic environments where data characteristics change frequently. These limitations could hinder the practical deployment of the method in real-world applications, particularly in scenarios demanding high accuracy and adaptability.